Hello everyone, this is Zach. Today I'll be talking about linear regression. The goal of linear regression is to help to make predictions. So the prediction problem is about predicting the value of an unobserved response variable, which is sometimes also known as a dependent variable. And you do this prediction, make this prediction using one or more explanatory variables, which are also known as independent variables. For example, you might want to predict the box office sales of a new movie using some information about that movie, or you might want to predict the number of guests who will visit Disneyland using some information about the weather and maybe some of the marketing campaigns that have been running and so on. So linear regression is based on assuming a linear relationship between the response variable and the explanatory variables. And this is some mathematical notation that is used for linear regression. Basically, the y denotes the dependent variable, x denotes the independent variable, beta are the regression coefficients, and epsilon is the error term or the residual. Let's make things concrete by looking at a real example of predicting a student's quiz score, given how many hours the student studied. So if you look at the data, you'll see that plot the data, it looks like this. So the data basically shows that quiz scores seem to go up as students study more hours. The baseline prediction is basically taking the mean of the quiz scores. And in this case, this baseline prediction basically, if you have no information about how many hours a student studied, the mean is a pretty good guess of the student's quiz score. Well, we would like to know whether the number of hours studied has an impact on the student's quiz score. If you look at the correlation between the score and the study hours, the correlation is plus 0.85, which is a reasonably large positive correlation. However, you might want to study kind of more rigorously. If a student studies one more hour, what do we expect the student's quiz score to change by? So linear regression assumes that a 1 unit increase in study hours results in an expected increase of beta 1 in the quiz score, where beta 1 is the coefficient. Basically, this equation is the equation of a line. So for example, y equals to c plus m times x is kind of the standard equation of the line that you've learned before in high school. So basically the idea of linear regression is to fit a line to the data. Here are three different lines, blue, red, and green, that can be drawn. And perhaps the green line looks like it fits better than the other two. But this is not very nice because it's kind of based on an eyeballing or kind of a guess. Is there a way to rigorously decide which is the best line, the best fit to the data? There is a method which is based on using the sum of squares of residuals. And this is the definition of the sum of squares of the residuals. Basically, you take the ith observed value minus the ith predicted value and you square it and you sum that up. The best fit line, as defined using the method of ordinary least squares, is the line which minimizes the sum of squares of the residuals. And if you calculate the best fit line, you'll get the purple line shown here. And you can see graphically that the purple line seems to fit the data a little bit better than all of the others. And indeed, if you calculate the sum of squares of the residuals, you'll see that the purple line minimizes the sum of squares of residuals. To find the best fit line, you have to use the LM function as shown, and the general syntax of the LM function is shown here. Basically, you have to give the data, which is the data frame. You have to specify in the formula the response variable tilde whatever explanatory variables there are. When you want to make predictions, you need to use the predict function on the model estimated by the LM function. If you're trying to predict for the observations that you use to estimate the model, then this is how you do it. But if you're trying to predict for new observations, for new data that you didn't use to estimate the model, you have to use the new data function. New data argument. Alright, now let's look at the summary of a linear model fit. If you use the summary function on a model, you'll see quite a bit of output that looks like this. I'm going to focus on the output in the blue box, and let's make it bigger. So this output actually looks like this. It's actually a table. So I copied the same information and put it explicitly in a table, so you can see the grid lines and how there is a table. The last column is the significance codes. So you can see each row of the table is one of the explanatory variables, and you have these different columns, the meanings of which are here, right? So I think the most important thing to know is the two important columns are the estimates, which are the coefficients, and the p-values. So if the p-value is very, very small, then the variable is statistically significant, and we expect that there is an effect of that variable on the response variable. So we don't always have the coefficients being statistically significant. So for example, for model 2, you see that the p-values are rather large and there are no significance codes. So this means, although it seems like height has a slight positive effect on scores, this is probably due to random noise and is not a reliable kind of finding. And if we repeated it on a similar set of students and scores, probably this finding would not appear. Let's also talk about factors. So sometimes we need to estimate or make predictions, and some of the explanatory variables are discrete. That means they're not like measurable quantities, but there are only a few possible values of these variables. So what the LM function does to handle this situation is to use what is called dummy encoding. Basically, it creates some new dummy variables to model all possible values of the discrete variable. So for example, if we have a race variable which has 3 possible values, say white, black, and other, what would happen is that we would create extra columns. There will be one of the values will be the so-called reference level, and for all the other levels, we'll create extra columns, one extra column for each other value. So if you look at the output of the Lm function when there is a discrete variable, you see that in this case there were three colors. So blue was chosen as the reference level. It's not listed. And you have values for green and red. So green and red in this case seem to be slightly lower scores, but this result is not statistically significant, so it could have been random. Alright, that's all for this lecture. See you next time. Bye.